Let's do an example of a hypothesis test involving the difference between means of two populations. The example I've chosen is an exercise from our textbook, number 16, from section 8.1, and it says that there is going to be a test of customer satisfaction with holiday gift purchases, depending on whether they purchased them online or they did walk-in, whether they went to the store in person. Turns out that the online purchasers numbered 30, and the average satisfaction rate was 90 out of 100, and the standard deviation, which we're assuming we know somehow, is 3.4. The walk-in traffic numbered 31 customers, and their satisfaction level averaged 88 out of 100, and their standard deviation was 3.5. Now, as it happens, the claim is that mu1, the satisfaction level of online shoppers, is higher than mu2, the satisfaction level of the population of walk-in customers. This is an incautious way to state this because automatically this can't be the null hypothesis. The null hypothesis needs equality. So our null hypothesis has got to be the opposite of the claim, that mu1 is less than or equal to mu2. And our retailer's claim then becomes the alternative. So let me label that. That's the claim. All right. So let's proceed to check this at the 1% level. At the 1% level, if you go to our calculator and we check this, 99% below, 0 and 1 for our standard distribution, 2.326. 2.326. Okay, so here's our 1% area, and as long as we get a statistic that's below this critical value of 2.326, then we do not reject the null hypothesis. And if we don't reject the null hypothesis, that goes contrary to the claim. All right, so let's check. The statistic in this case is a z-statistic since we know the standard deviations, and it looks like this. We take x1 bar minus x2 bar. That's the difference of those two means. We subtract mu1 minus mu2, okay? And we combine the standard deviations in a rather awkward way. Sigma 1 squared over n1 plus sigma 2 squared over n2. Okay? So that's what we're looking at. If we start plugging in, let's see what our statistic turns out to be. So x1 is 90, x2 is 88, so the difference is 2. And according to the null hypothesis, we're assuming the possibility of equality, so that's just 0, mu1 and mu2 being equal. That's an important point to catch. And then down here, where we have some significant calculation to do, we've got sigma 1, which is 3.4. That's going to get squared. And then we're going to divide by 30. And 3.5 squared. And that's going to be divided by 31. Okay? Feed this all into your calculator. And you carefully work out and discover that you get 2.26. Okay? Now, where is 2.26? Well, it's here. It's not in the rejection region. So, we do not reject the null hypothesis. which is too bad for our retailer because that goes contrary to his claim. If we didn't know the standard deviations and we had to use S1 and S2 instead as statistics, we would have to go over to a t-distribution, and it's the same calculation, except now watch out, if you're going to be using t, you have to pick degrees of freedom. It'll be either n1 minus 1 or n2 minus 1, whichever one is smaller. And there's a special situation that arises where you don't use this formula, but you use a more complicated formula if the standard deviations are assumed to be equal, and you have to compute a pooled standard deviation. I'm not going to do an example of that sort of thing right now. This is enough to get you started, and it's more hypothesis testing.